Okay, welcome everybody. We're very happy to have Nima Afkhami-Jeddi from Chicago tell us today about exploring conformative theories via bootstrap deformations.
All right, thank you very much. Thank you for having me. So today I'll be talking about this paper that came out a few weeks back. So the talk will involve, let's go straight to the outline. So the talk will start with a review, and I know that most of you are, I guess all of you are experts in the Bootstrap, but please bear with me a little bit so that at least I can establish some notations. Oh, that's a good way to start. Technical difficulties. Can you guys see my slide again?
Cannot see your slide.
You cannot see my slides.
No.
Okay, let's see. Let me try this share thing again. I'm using a second display, and sometimes I knock the cable out. Okay, can you see it now?
Yes.
Okay, great. So I'll start with some review. That'll be maybe somewhat slow, but it'll help me establish some notations so that we can have a common language. And feel free to stop me at any point if I'm not being clear, and we'll try to discuss things in more detail. All right, so I'll start with a review, and then I'll discuss how to think of the Bootstrap as some constrained optimization problem. And I'll describe how finding the solutions to these optimization problems will end up with the same results as you would get as if you were using SDPB. And then, having done that, I'll describe how we can deform these solutions and move away from regions that we can access with SDPP. So namely, we're able to foray into the non-unitary regions because positivity will not play a role in this optimization problem. Then I'll show some numerical results in 2 dimensions, modular bootstrap, and some results in 3 dimensions. And I'll describe some future directions and some things we're trying out at this point. Okay, and like I said, feel free to stop me at any point if I'm not being clear. All right, so the general bootstrap setup, I'll try to describe them in the most general setting I can. It typically involves, we start with some physical observable that has expansions in different channels. These expansions can come from the OP expansion of the 4-point function, or you could be considering the partition function of a CFT on a torus as an observable, in which case, you know, the different quantization surfaces will give you a different expansion. But in either case, you end up with an equation. Let's see if I can, yeah, you end up with an equation that is an expansion in one channel equals the expansion in the other channel. I'll try to keep my notations consistent, so I'll use C, F, and so on throughout the talk with the same notation. Here, F is some function that's usually fixed by the space-time symmetries of the problem. X is the coordinates that define the observable, and these C's are typically dynamical information about the theory. And here, the sums are over the 2 channels I labeled Q1 and Q2, and the quantum numbers appearing, which label the representations of the theory, are also dynamical information we're trying to solve for. So this is the general equation of the bootstrap in all cases that I know of. Now, for my purposes and for the rest of this talk, I will take the 2 channels, the quantum numbers that appear in the 2 channels, to be the same. This happens in all sorts of cases. For example, the torus partition function, or if you're considering 4-point function of identical operators, the quantum numbers that appear in the 2 channels will be the same, which will simplify some of the things we'll be talking about. It's not strictly necessary, and I'll talk about cases where you can relax that assumption. But for most of my talk, I'll take that to be the case going forward. So putting everything to one side of the equation, you end up with a sum over typically infinitely many things having to vanish. And let me call the difference between the two channels W. And typically this is infinitely many equations for infinitely many unknowns. Infinitely many equations because you can evaluate this observable at any point, any coordinate that defines the observable. And it's typically infinitely many unknowns because there's infinitely many contributions to the sum, which with different quantum numbers and so on. So the way we typically make progress on this is we try to extract information using the action of linear functionals. Let me abstractly call the linear functionals these curly FIs. So Fi is some abstract linear functional acting on the equation I described above, which leads to an equation that is no longer depending on the coordinates that define the observable. So no more ZZ bar or tau tau bar or whatever other coordinates define the observable we're talking about. And you have finitely many equations now, but you still have infinitely many unknowns. So this curly F, as I said, is the linear functional, for example, taking derivatives with respect to the coordinates and evaluating at some symmetric point. This is the functional that's typically used. It's not necessary, there's probably better ones, but this is the one I will choose to use. And in the rest of the talk, the notation will be that this label I will label the functional, and I'll take them to go from 1 to lambda. So this is the dimension of the functional space that I'll be considering. And also in the rest of the talk, A will label the quantum numbers that appear in the expansion. So for example, the scaling dimensions, the spin, or whatever representation the exchange operators can have in the expansion. So that's the notation. And this equation in the yellow box will be the one we'll be concerned with most of the time. Okay. Now, the logic of the bootstrap, like I said, it's finitely many equations now, but infinitely many unknowns. The logic is typically we make some assumption in this about this Q, which is the operators that can appear in this expansion. Say Q belongs to some subset of all possible things, Q bar. And what we try to do is we try to find a set of numbers, alpha I, such that alpha I Fi summed over is greater than 0 for all these quantum numbers that are in this reduced subset. If our theory was unitary, the coefficients of the expansion in this yellow boxed equation are positive, so you end up with a contradiction. So the Q bar, which you assumed included all the operators that appeared, will be ruled out, and that's how you typically carve out the space of available CFDs. This is a very standard thing that we do all as I'm sure you're all familiar with. But to be concrete and to try and pass over to the different formulation, let me consider the simplest possible non-trivial example of a conformal bootstrap problem I can think of, and that's the spinless modular bootstrap problem. So this problem is very simple. It arises when you try to consider the torus partition function of a 2D CFD. And you set the modulus tau bar to be minus tau. When you do this, the expansion that appears will have no dependence on the spin. All the H minus H bars drop out, and you just end up with H plus H bar. So this is a relatively simple tame problem. It's a one-dimensional problem in a sense that I'll describe in a bit. The partition function has an expansion in terms of characters, conformal characters. These are the kinematic functions that I was describing before for this type of problem. And here I've written an explicit expression for them. These are the so-called reduced characters. It's just convenient to work with the reduced partition function, which is related to the original partition function by some multiplication. It just makes modular invariance, which is just tau goes to minus 1 over tau, the crossing equation, just simpler to work with. The functionals, here I'm writing it up explicitly. There exists some differential operator that acts on these functionals in a nice way. And the end result is that you get a set of simple polynomials as your functionals. In this case, they turn out to be the Laguerre polynomials. So anytime I write this curly F, now for this particular problem, I'm thinking of just some simple odd labeled Laguerre polynomials. Okay, So this is the setup. Now let's go back to the equation we had above. So acting with these functionals on this equation, we end up with the equation that now, instead of labeling it with A, I'm labeling it with the quantum numbers that appear, which are the scaling dimensions. And to rule out the parameter space, you can choose what it is that you want to look for. I will choose to try and find a bound on the lowest operator above the vacuum contribution. So what you try to do is you try to find a set of numbers alpha I such that alpha I fi is greater than 0 for all delta bigger than some delta gap, and its contribution is also positive or vanishing on the vacuum to try and get a contradiction. And typically, we do this with semi-definite programming. The collaboration has developed some very nice software, the SDPP, and you can try to map out the parameter space of allowed 2D CFD partition functions. And this is typically how we proceed. This is all very standard stuff. I'm just maybe using different notations because everybody uses different notations in different papers. So if there's no questions about this, let me proceed and try to describe the extremal functional. So for my purposes, the extremal functional comes about when we try to find the largest region in the parameter space where the theories are out. So in the case of the problem I described above, when you try to find the largest such a delta gap where the theory is allowed, meaning you can't find a functional, I call that resulting functional alpha I dot fi the extremal functional. And we can make some observations about this particular simple case. So given lambda such functionals, we find that the extremal functional always has a single 0 at the value of the delta gap. And it always works out in this particular case to have lambda over 2 minus 1 double zeros. So on the right here, I've plotted sample functional. So you can see there's a single 0 at the delta gap, and there's a bunch of other double zeros, double roots. And what you find is that the position of these roots correspond to the solutions to the truncated bootstrap equations. And we will show why this is the case. But this is just an observation for now. So this fact motivates that maybe instead of trying to do semi-definite programming, we can instead try to parameterize the problem directly in terms of these roots, which, because they're the solutions to the truncated equations, there's some approximation to the CFD data itself. So that's how we'll proceed.
Nima, just a clarification. So
Yes.
The functional also vanishes at 0, the identity.
That is correct. The functional also vanishes at 0. Yes.
Thank you.
Yeah, I guess it's not. I mean, does it look like that? Yeah, it does look like that on this plot, but the vacuum contribution in this particular case is a different character because it has the null states removed. So even though this looks like it's 0, I think the reason is because for some large C, the vacuum character and the other characters are exponentially close. But yes, in general, what we find is that the vacuum contribution is 0. And here, I guess I sweep something under the rug. I only wrote down the characters for the non-trivial representation, the non-vacuum representation. The vacuum representation would have a different character here. In the other problems I'll consider when I go to the correlation function, that subtlety is not there. Okay. Now, so like I said, this motivates solving directly for the spectrum. But I don't want to just solve the truncated bootstrap equations, because in this accident that happened here, where the number of number of double zeros was nicely lambda over 2 minus 1, and I'll describe why that's nice in a minute, won't happen in general. So I would like to write down the most general optimization problem. And I find it convenient package this whole business in terms of some Lagrangian. So let me write down a Lagrangian that optimizes the vacuum subject to some constraints, which I'm imposing using some Lagrange multipliers, which I'm calling C mu and C tilde nu. So let's try to unpack this a little bit. So I'm solving the optimization problem where I try to optimize the vacuum. I am imposing, right, let's see. Does the cursor show up now?
Yeah.
Okay, good. So this equation is imposing that I have zeros in the extremal functional. I don't know what those things are, but this equation below it is imposing that I have double roots where the double roots are. So notice that mu index goes from mu to the total number of zeros, and the new index goes from 2, because this first root that appeared was a single, and the rest were all doubles. So in this simple case, the Lagrange multipliers are simply imposing these conditions on my extremal functional. And you'll notice that if you start with this Lagrangian and you dualize it, that is, you treat the alpha i's as Lagrange multipliers and make the additional technical assumption that the extremal functional doesn't have any triple roots, any higher order roots, you actually find a dual problem that is the truncated bootstrap equations, which explains why the output of SDPP, the extremal functional that I get, if it really is optimizing this problem, the roots of the extremal functional directly correspond to the truncated bootstrap equations. So let's move on and try to think about what the solutions to the optimum of this Lagrangian look like. So at optimum, optimizing with respect to all the parameters, I end up with a set of equations varying with respect to different coordinates. The one here on the left, this is the truncated bootstrap equations that we just talked about. And in addition, you have 2 other equations that impose the roots. There is lambda such equations for the first one, lambda over 2 for the second one, and lambda over 2 minus 1 for the third one. At the minus 1 because there is one single root and the rest are doubles. So in total, I have 2 lambda minus 1 equations. And in principle, I'm solving these for the scaling dimensions, delta mu, the Lagrange multiplier C mu, which turns out to correspond to the OP coefficients, approximate OP coefficients in the same way that the scaling dimensions correspond to, the roots correspond to the approximate scaling dimensions. And so I have lambda such variables here, and I'm also solving for the alpha. But the overall normalization of the extremal functional doesn't matter. So let me take away one variable by setting alpha 1 to be 1, for example. So I have lambda minus 1 variables here, so the total number of equations and unknowns always matches as long as you manage to write some Lagrangian that you're optimizing. It's just for me, it's a bookkeeping device. You can try to just write down the equations you need to solve, but this helps me keep track, especially when I move on to the more complicated case of correlation functions where there's multiple channels and so on. That we'll discuss in a minute. However, in this simple case, notice that the 2 equations, the 2 sets of equations, the truncated bootstrap equations and the equations that impose the roots sort of decouple. The reason is because I can explicitly just write down what the alpha is once I have the solutions to the truncated equation. Explicitly, it's the kernel of some matrix that I can write down. I can make a matrix with vectors that correspond to these functionals. And this is the lambda by lambda minus 1 matrix. So there are the null space of this matrix is always fixed uniquely up to some rescaling. And there's always a solution. Essentially, I have a d-dimensional space with d minus 1 vectors, so I can always find a plane. So there exists a unique solution. So in principle, what I can do is I can just solve the truncated bootstrap equations. And in practice, the way you go about solving this thing is, in this simple case, you can just solve the truncated bootstrap equation. So you make, these are some nonlinear equations for the deltas, and some linear equations for the C's. So you make some initial guess for the deltas and you try to solve it using your favorite method. I'll use Newton's method to solve these nonlinear equations. And a couple of years back with Tom and Amir, we carried out this program and we were able to push the spinless modular bootstrap to some large number of functionals. Works very well. And you can explicitly, after solving the truncated bootstrap equations, you can explicitly write the extremal functionals. And as long as you have the functionals, you have some rigorous bounds on this space. So the bounds that you get out of this are just as good as what you would get using the traditional bootstrap methods. It has the added advantage that it's a couple of orders of magnitudes faster than trying to go about it in the traditional way, which is using semi-definite programming. So that's why we were able to push it to some large number. Yeah, is there any questions about this? Because I think now I'm going to move on to the more complicated case about the logic of what we did here. Okay.
Maybe a question.
Yes.
So guessing, I just would like to ask, why is it so efficient? So if I had to guess delta mu and delta mu, the set of delta mu is completely unknown, wouldn't this be an extremely hard problem?
Yes, that is true. So in this particular case, because the problem is so simple, you just have a one-dimensional. I just mean there's only delta is the only quantum numbers that appear. In this case, we made the observation that the scaling dimensions as I increase lambda seem to follow a simple pattern. You can use that pattern to try and guess what happens as you increase lambda to the point where you can, the way we did this was iterative. So you start with 3 operators, and that's easy enough to solve. It's just some 6-parameter thing. You can make up some guess. And then you can use that to guess what the next, if I increase lambda to 8, what does that look like going from 6 to 8? And you can do that. And in fact, doing this for a while, you'll notice a pattern and you can use that to jump lambda by like 40, 50. And you can use this to iteratively go to larger and larger space of dimensions. This will no longer be the case when we go to the correlation function and we need some other method of finding some initial conditions. It just so happened that for this particular case, it was very simple to guess initial conditions for this nonlinear set of equations. And, this will be some bottleneck when we try to do, like I will not be, when I consider the more interesting problem of correlation functions, I will not be able to push lambda to some large number. In fact, I'll be only able to deal with cases where I have some other means of getting the initial conditions.
Thank you.
Yeah. Okay, let's move on to the more interesting problem, which is the scalar 4-point function. So the 4-point function has some expansion. You can choose to expand in one OP channel versus the other OP channel. This is an expression that Chamfurter is familiar to everyone. You have an expansion in terms of some conformal blocks, which are known in even dimensions explicitly, but in all dimensions, there exists some recursion relations that efficiently compute these in terms of some poles times some polynomials, which people here have worked out. People have written nice software packages for computing these things, so I'll be explicitly using this. And the functionals I will be using will be the standard derivatives with respect to z and z bar. And the bootstrap problem I'll be considering is to optimize the scalar gap. There's new ingredients here because now in addition to the scaling dimension, there's also the quantum number of spin. And so this adds the complication that instead of just one functional, there will be many extremal functionals, one corresponding to each spin. And it is not clear, where the zeros that correspond to different functionals, where they go and so on. And it's difficult to make initial guesses. It's not as simple a problem as the spinless modular bootstrap. So we need some new way of generating initial conditions for the nonlinear equations we're trying to solve. And on top of that, the number of single and double roots, it changes with changing lambda, the dimension of my functional space. So in general, it's a more difficult problem if your goal in life was to try and go to some large dimension of functional space. But there's other things that we can do, which I think are useful.
Can you explain this point about not single double roots changing? So
Yeah.
how it's happening?
So as far as I can tell, it's just an experimental observation. As I increase the dimension, so the reason I'm saying this is I can use the traditional methods using SDPB to try and obtain the extremal functional. And as I change the dimension of the functional space and I extract the roots of the extremal functionals for different spins, so there will be an extremal functional for spin 0, spin 2, and so on. When you look at the pattern of zeros, it seems to be all over the place, especially in the higher operators. So the low-lying operators will typically converge. So the scalar gap will converge. The first few operators will converge and they'll be stable. But as I increase lambda, there will be new roots that appear in the higher end of part of the spectrum, and those ones aren't stable.
But are they single or double roots?
They are typically double roots, but sometimes there will be a single root at spin like 12 and for one lambda, and as I increase lambda, that single root will disappear and it'll appear at a different operator. So that can also happen, and it does happen.
But where do the single roots lie? Do they lie at the unitarity bound? Where
they typically lie at the unitarity bound, yes.
Okay.
Okay. But everything I said is true, but this is still an optimization problem. I can still write down some Lagrangian, which I'm writing here, which will have additional labels now, scaling dimensions and spins. And I can play the same game. I can try to optimize this Lagrangian with respect to all the variables. The variables will now, I labeled them delta D and delta S corresponding to the single and double roots to distinguish them. There will be the truncated bootstrap equations, and there will be equations imposing double and single roots on the set of equations. This just follows from the Lagrangian that I wrote down above. And again, I will choose to normalize my functional such that alpha 1 is equal to 1. So I have lambda plus ns plus 2nd equations, and I can solve this for the alphas, the C mu's, the delta gap, and the delta d's variables. And these numbers will always match. I mean, they had to. I started with some Lagrangian.
But I'm sorry, Nima, this point about
Yes.
single roots, it always confuses me because
Yes.
These roots at the unitarity bound, how
Yes.
do we physically interpret these single roots at the unitarity bound?
Yeah, that's a good point. Well, what I'll say is the following, that these roots are necessary in order for these scaling dimensions that I claim are approximate solutions to be a solution to the truncated bootstrap equation. I suspect that as I increase lambda, these roots need to disappear, but the fact that they are necessary for them to be some solutions to the truncated bootstrap equations, it's one possibility that this is an artifact of the fact that I'm considering some truncated equations instead of the full, sum over the spectrum. That's one possible explanation. It's possible that if you kept more and more operators, you would need less and less of these single roots.
So there's no option that, for example, if you just by hand disallow single roots for all spins except for spin 2, then you say that you just won't find a solution.
In general, no. This is what I found using SDPP. I mean, the numerical analysis that I do, I mean, it happened that I'm going to consider the 2D 4-point function. And in that case, it happened that I found just a stress tensile single root. But when I increase lambda, new operators appear, and I don't know what to do about that except to keep them if I want to continue. But I don't have a good physical reason why they have to be there, aside from the fact that they just could be there because I'm considering the truncated equations. This isn't a full-blown CFT. Okay, so, and I made a point of saying that I don't know how to get initial conditions, except I do when I'm considering unitary cases. I can always use the traditional Bootstrap methods to find some initial conditions. So I can use semi-definite programming, do some bisection, find my extremal functional and extract those roots. And those roots will serve as some initial conditions for this finding the solutions to these nonlinear set of equations. And maybe I didn't make it a point to say before, but you don't really need a good guess for the C's and the alphas. Those are very simple to find because the relationship is linear, so you don't really need a good guess. You only need a good guess for the spectrum of the theory when you try to solve these equations. Okay, so let's try to describe a concrete example. So let me consider the simple case of a 2D CFT identical scalars. This gives rise to this famous Kink plot where you have the Ising sitting at 1/8 and 1 in when plotted against delta phi and delta phi squared. So the procedure is the one I just described. You use SDPP and bisection to try and land on the extremal functional and use this, extract the roots out of these functionals and use these as initial conditions, and then optimize the Lagrangian. I should say, you don't really need to land directly to this extremal functional. If you recall, the delta gap for me is one of the parameters that I'm varying. So I don't need to get that close. Once I'm close enough, optimizing this thing will automatically optimize the delta gap also. So it eliminates one step. This bisection step is no longer necessary. So as long as I'm close, I use that as some initial conditions and I optimize the Lagrangian. And I find that any extremal functional I find out of SDPP will always give a viable initial condition and will always converge to the solutions of the equations that I wrote about. And at this point, we can do the following. We can use this initial condition that we find, the solution that we found, as the starting seed for a solution where I've deformed some parameter that defines my problem. So one obvious candidate is to deform the external operator dimension delta phi. And so I deform it a little bit. I use the previous solution as a initial conditions, and I find that I can easily converge to the extremal functional at a nearby point. And the convergence is really fast, and this allows me to explore the space of extremal functionals relatively quickly. So in this particular case, I can see that I move along the unitarity line and get to the kink, and I can explore the space of extremal functionals. But I will notice that, I remember I'm keeping track of all the approximate CFT data. I'm keeping track of the OP coefficients and the spectrum as I do this. And what one will find is that as you get near the kink, some of the OP coefficient squares, they become negative. And at that point, or they go through 0. And at that point, you have a choice. You can either set those operators to 0 and try to flow along the unitarity curve, or you can just let them be and you're just optimizing some Lagrangian and just continue past that point with negative OP coefficients. So I choose to do the second option and just move past those points. And if you do that, you can.
Nima, can I ask
yes.
something else which worries me?
Yes, yes.
It's so you mentioned, okay, there are the single roots, double roots, but as you move along this yellow arrow,
yes,
can this happen that some roots collide? You know, single roots become double roots or whatnot. So
yes, it can, and I'll describe that.
Okay.
Yes, it does. So let me give some numerical data. So if I start with the simple case that I just described above, so this blue curve in this figure corresponds to what you get out of SDPP. This is my starting point, and the filled in circles correspond to the single roots of the extremal functional. So these aren't the parameters in the theory. I'm literally finding the extremal functional, finding the roots and plotting them. I'm distinguishing this because the equations that I had above had a certain number of parameters. Those are the ones that I'm varying and I'm solving with respect to, whereas what I'm plotting here are the actual roots that come out. So obviously it necessarily has the roots that are parameters, but it might happen, like Slava just said, that, well, some new roots might appear and you're not parameterizing that correctly. So in this plot, I'm plotting delta phi on the x-axis, and there's an observation that was made by Miguel Polish and Alshok back in 2016 that doing this and following extremal functionals to non-unitary regions, you can connect the Ising CFD to the Yang-Lee CFD. I mean, this is just some evidence for this, because when I look at the roots that appear in this functional as I do the deformation and I get to -2/5, I mean, here we have the advantage that these are minimal models. We know everything about them, so we can just compare the candidate spectrum that we get. And we find that, you know, at delta phi is -2/5, there is a single root at -0.38, which is the operator we expect there to be. In addition, I'm computing the OP coefficients correctly, so I can use the Ward identities to extract the central charge. And I see that, you know, at -2/5, it's roughly -4.7, which is numerically close. I should say that for these plots, I took lambda to be 8 instead of being something large, and I'll explain the reasons for that. So given that the dimension of my functional space is small, the fact that I'm matching like 3 or 4 operators that is consistent with what I get out of Yang-Lee is some evidence that I really am connecting Ising and Yang-Lee. But you might wonder, well, what happened here in this region? Why is there such a jump? And the reason is because in order for me to make this flow work, I had to do something. And what I had to do was, when I started initially deforming this extremal solution, I find that at around -0.09, what Slava described appears. So I get a new set of single zeros that appear in my functionals. So what's happening is if I look at the extremal functional for spin 2, I find that at one point the functional dips below 0 and I get 2 new single roots. And at this point you have a choice. You can say, well, okay, I don't really care about the extremal functional because I'm in the non-unitary region. I don't have positivity of OP coefficient, so I can't interpret these extremal functionals as rigorous bounds anyways. And you can try to continue. And if you do that, you find that the deformation terminates. The operators either shoot off to infinity, and you can't continue past that point. Or the other thing that you can do is you can say, well, okay, I can try to go back to where these pair appeared and try to add a new double root to my parameters. So modify my sets of equations and my parameters by adding a new double root. And you find that, to me, miraculously, when you do that, this still is a solution that optimizes the Lagrangian. It's not obvious to me that this had to be the case, but it turns out to be the case in every case that I encountered a new pair appearing. I can always add a double zero and find a new extremal solution. So that's what happened here. I added a new operator to the spectrum as I deformed. And doing this allowed me to just continue deforming past the delta phi equals 0 and continue past into the non-unitary region. And in addition, like I said, while doing this, you're keeping track of the OP coefficients and all the operator spectra that appear in the theorem. Is there any questions about this?
So could you add 2 single zeros instead of 1 double? It's a bit not clear to me.
You can. Well,
that would be yet another way to continue, but you just have to make some discrete choices.
Yes, that's right. You have to make discrete choices, and I'll talk about the uniqueness of this business in a bit. There is no guide as to what you're supposed to do. The thing that I took to be my guide is I would like to do the thing that will allow me to continue this deformation.
Sure.
But this is something that needs to be thought about, the uniqueness of flows and different starting points and so on.
I had also a question which may have the same answer.
Yes.
Which is, what is your definition of an extremal functional at this, or an extremal solution at this point?
Extremal solution is, I guess, something that I can continuously connect to what we would normally call standard extremal functionals. It's a solution, it's an optimum to this Lagrangian that I described above, that we can take that to be the example. I mean, this Lagrangian will have many optima, I suspect.
Exactly.
And not all of them will correspond to theories. The hope here is that because I started with something that I do know correspond to a theory, hoping that different theories might correspond to connected solutions while I deform these things. And it turns out there's some evidence for this being the case. There's evidence for this in the modular bootstrap. I mean, you can take this as evidence because the spectrum that I'm extracting does seem to be consistent with Yang Li, and I know that I started with the Ising. And in 3 dimensions, I'll also provide some evidence for this being the case. But yeah,
I agree that it all works. I guess extremality usually implies some, well, the way it's used in the bootstrap is there's some like minimal set of operators, right? Some sparseness in the spectrum.
Yeah, I should say, I mean, you can do the other thing that people have been doing, which is just to try and solve the truncated bootstrap equations. The solutions you get out of the optimum of this Lagrangian are different because you're not just finding solutions to truncated equations, you're also at the same time trying to find some functional, and those 2 equations are not decoupled in general. They were decoupled in the spinless bootstrap case, but in this case, because the number of zeros don't work out so nicely, they're not decoupled. So it's a different set of equations you're solving. And I find that it's necessary to solve them both, otherwise you will not be able to do these deformations.
Okay, thanks.
Sorry, Nima, I got a bit confused. Is in this picture, in this zoom in, are there 2 single roots appearing or 2 double roots?
No, these are 2 single roots. Sorry, they're 2 single roots. And what I do when I go back to this figure is I go to this, let me see, I go to this position and I impose the addition of a new double root, and I add that to one of the parameters that I solve for.
Oh, I see. So this figure is not the same figure as above. It's different.
Yeah, it's a different figure. So up to this point, it's the same, but then at this point, I add a new operator.
Okay, all right. Thank you.
But wasn't there already wasn't there already a double root that became 2 single roots?
No. This what happened was you had a functional. Let's see. You had a functional that as I continued, it looked like this, and it went down up to the point where it crossed 0. That's how these new single roots appeared.
All right, thanks.
So I described that I can deform this thing in the dimension of the external delta phi, but in principle, there's nothing stopping me from deforming in any other parameter that I choose. So here I choose to deform this in terms of the space-time dimension D. So I can take this Yang Li solution and I can deform it in D, doing the same thing I did before, using the previous solution as some initial condition for some new deformation. And it turns out I can do this and I can find a solution in D equals 3, which is some continuation of the 2D Yang Li. And here I'm plotting what the spectrum looks like when you do that. And then what I can do is now I can take that solution in 3D and I start deforming the external delta phi. And I can plot what the spectrum looks like when I do that. So here, the 2 figures, I'm plotting the different roots that appear, and the plot on the right is just the scalar root. And the reason I'm plotting just the scalar root is because I can compare it with calculations people have done using other methods, which is, for example, the epsilon expansion. This little blue square is the predictions from the epsilon expansion. So at this point, all I can say is, okay, look, there's a root that goes through what the predicted region is. So perhaps there's some evidence that this might be consistent. But I could do one other thing. The other thing that I could do is, instead of starting in 2D, deforming into 3D, and then deforming, I can have a different starting point. So I can start directly in 3D, finding the extremal functional corresponding to Eisen, like we did in 2D, and then deform that. And if you do that, so here I'm plotting what happens when you do that, and notice there's all sorts of mixing phenomena happening where operators will join, collide, and become a single operator over here, or maybe it's better. So the plot on the left corresponds to all these spins, but the plot on the right, I'm just plotting the scalar roots. You can see that the roots merge, and you need to account for that. Otherwise, you're unable to continue the deformation and so on. And this makes it a bit tedious, because the way I do this is I do the deformation, I have mathematically run some code, and I come back and it's stopped, and I have to plot the zeros and look what happened, and then it's like, you have to add a new operator. So it's somewhat tedious, and this is sort of the bottleneck for me in increasing lambda. I could start with some larger lambda, but then this phenomenon occurs much more often. So writing some code to automate this will go a long way towards exploring these extremal flows. But in any case, I can do that, and I see that the deformation in this case, when I look at the scalar operator spectrum, also has a root that goes through the same point. So you have these two. So this orange is this thing over here, and the black is this thing over here. They both go through the same position, and that for me is some further evidence that perhaps I can access this non-unitary theory in 3D. However, there's a downside where, like, when we do the ordinary bootstrap, there's kinks and there's other features you can try to use to say that I've reached some physical theory, whereas here I don't really have anything to go by besides other calculations that tell me there might be a unitary or non-unitary theory here. But if I take that as a given, I can extract more information than those people can by looking at the extremal functional and the OP coefficients that I can extract in this way. So I just take this as some evidence that maybe there's something to explore here, and we should try to go to higher lambdas and see whether we get better and better CFD data.
I missed the first part of the story. Did you say that you can go from 2D to 3D?
That is correct, yeah. I can go from 2D to 3D, just continue the extremal solution. And
usually one says that if you start with minimal model or with Virasoro 15 2D, then it's extremely difficult to depart, even to go from 2 to 2 plus epsilon, because there are going to be potentially some weird things happening. You don't have any difficulty there?
I did not have any difficulty, and as you know, I didn't start with Virasoro. I mean, I just used the global blocks. So the Virasoro, as you know, when you use the Bootstrap in 2D and use the global blocks, the fact that there is Virasoro will emerge dynamically as far as Bootstrap is concerned.
Sure. So you started, what did you do in 2D exactly? You did the exact spectrum, and you
I found
as an initial approximation.
I found oh, you mean in terms of the blocks? What did I do? Yeah, I used the rational approximation for the blocks. And
no, but I meant, how did you find the extremal solution in 2D? Because you guess you have to have high quality extremal solution in 2D.
Oh yeah, I mean, well, depends on what you mean by high quality, but I find the extremal solutions to convert, like I find the optimum of this Lagrangian that I described to some high precision, and I deform that indeed. I don't go to some high value of functional space, but any of the extremal solutions that I found correspond to, sorry, any of the optima of the Lagrangian that I found corresponds to some extremal functional, and I can deform that in any.
What is not obvious to me, I thought, but you seem to be saying otherwise, that if you just start from the spectrum of primaries or quasi-primaries in 2D, and you use that as a seed to construct an extremal solution in your sense, a truncated one.
Yeah.
It's going to be hard, but you managed to do this.
Oh, sorry.
When
the way I did
the initial approximation.
Yeah. So what I did was I take the previous solution as initial conditions for the deformed equations. So at every point in these deformation plots, so the point at here provides
what was the initial
constraint.
point in 2D? Initial
Oh, it was
point
Yang. It was Yang Li. It was the Yang Li 2D CFD extremal functional. So it was this point over here. I took this point.
Ah, I see. Okay,
And I
okay. So
deformed
you
that.
didn't find it. You found it like this. Okay. Fine.
Yes, yes.
Here
But
it
I
is.
did it two ways. I also did it in three. I started directly in 3D. I used the 3D Ising extremal functional, and I deformed that also. And I find that they both of these initial starting points end up with a root that goes through this point that is predicted by the epsilon expansion. That's what I was saying.
I was just wondering if there was some trick, some nice way to find the 2D functional using the fact that the 2D Liang CFT is exactly solved.
No, that's the thing. I can't, like, I know everything about Yang Li. I know all the quasi-primaries, but I can't use that. Oops. I can't use that as a starting point because I'm not solving I'm not using a full theory. I'm using the truncated, these are the solutions to the truncated equation. So the exact answer isn't right.
Yeah.
Okay, let me skip the modular bootstrap stuff. It's essentially an identical story, except instead of deforming the external scaling dimensions, I am deforming the central charge. I can play a similar game. I can do deformations. And in this case, also, I'm able to access some non-unitary region, which looks, you know, the operator spectrum is again consistent with Li Yang. Let me try to describe some other things that might be more interesting and perhaps more useful, which is everything I've described here didn't really rely on the simplicity of the problem. I could always write down some optimization problem, some Lagrangian to try and optimize. And namely, I can consider the mixed system of correlators. There again, you can recast this business of bisection and finding extremal functionals as some optimization problem. Whereas now, instead of having some one-line equation, you have a matrix equation. And in addition, you have additional channels. You have the odd channel and the even channel, and you have the spins and so on. For example, for the simple case of the Ising island, you consider some mixed correlator. There are more parameters that you need, but the same principles apply. You're just optimizing some Lagrangian. And the reason you might want to do this, besides deformation and other parameters, one reason you might want to do this is because this is orders of magnitude faster. So, you know, if your goal in life to try to map out some island region, instead of laying down some grid and trying to see whether some region in the grid is allowed or disallowed, instead, what I'm advocating is maybe you should try to find the beach of the island, find the boundary, find the extremal solution, and then deform along that, because that's a much faster thing to do. So, you know, you can, again, write down some Lagrangian, you get a set of equations, which I've written down here. Here is a 2x2 matrix. In general, it's something more complicated. So the procedure would be the following. You start with STPB, you do bisection, you find the boundary of the island.
Nima, there is something wrong with your slides. They're stuck on some page showing modular bootstrap deformations.
Oh, no, okay. Sorry about that. Let's see. Did that fix it?
No, now we see Ising Island.
Okay, good. So I didn't really say much. The slide here is just what I said previously, just in words. Here is a set of equations that correspond to the island, and the procedure would be the following. You do bisection, you find the extremal boundary of the island. You probably have to do this twice because the top and the bottom of the island correspond to the different extremal solution. And then once you have that point, you can very quickly move along the extremal solution, even if your equation has a lot of parameters. I mean, for the case of the spinless modular bootstrap, we were able to push this to 1,000 operators, and that didn't really, like, you know, it would take orders of minutes on a laptop instead of on a cluster. So as long as you can give me the initial conditions that correspond to one boundary of the island, you can deform this and map out the rest of your island. So this might be something of interest to you. And on top of that, you can try deforming the island in, like, you know, in space-time dimension and so on. And that way, at least that can be a feature that you can try to say, well, I have a theory here, but that's not something I've explored. Is there any questions on this before I move on to just closing?
Can I ask a question?
Yes, please.
Yeah. So do you like have you measured like how fast you can move along the beach of this island? I guess one worry that I have is once you start like using the extremal flow method to like go from one point to the other point of the beach, and then like at some point you're gonna have like to add and subtract off some double zeros. So as lambda gets higher and higher, then you're forced to like do this more and more often. So you're forced to take smaller and smaller deformation along the way, right?
Yeah. Let me make the following comments. So each initial step of conversion, for a problem with like 100 some odd parameters takes maybe like 4 or 5 seconds. So each point comes at a cost of 5 or 10 seconds. The thing that takes a long time, like you say, adding new operators, the reason it takes a long time is because I have to sit there, monitor where a new root appears, and then add that by hand. And that takes a while, but this is not some principal hurdle. This is just some engineering hurdle. Someone better than me at coding can sit down, detect these new roots automatically, and have these be automated. And once that business is automated, then every point takes order of maybe a minute if your lambda is really large. And exploring these islands would be easier. I do agree with you that this is an annoying thing to do, but if it's automated, then I don't think it's a problem.
Okay.
I should say that I haven't tried flowing across the island yet, but I have found that the extremal solutions are the solution to the Lagrangian that I wrote down before.
Yeah.
So this is, in principle, I don't see anything wrong with attempting this.
Sorry, can I ask?
Yes.
I think many of the words you just said were also said by Miguel Paulos and Shir Al-Shok when they wrote their extremal functional paper, that we were able supposed to move along these bounds quickly.
Yes.
And also, and it worked very well in one-dimensional problems where you don't have a sum over spins.
That's right.
But indeed, sometimes there would be new operators appearing, and that would have to be coded by someone smarter than them or with more time than them. And then they never got around to doing it, I think, and nobody ever did it. And now you seem to be saying exactly the same words.
But
is there some qualitative difference between what you're doing and what they're doing? I guess is my question. And is it going to be easier for you than it was for them?
Well, I don't know exactly what they did and why they stopped doing it. I've sort of done, I think maybe they were using Julia, and it's not something our community as a whole has picked up a lot. Well, maybe some people have. I've used Mathematica, and with the submission of this paper, I also submitted the Mathematica file for people to play with. So hoping to make it a bit more open source so that people who are interested in doing other things with this technology can, have a starting point, but they don't have to do their own coding from the beginning. So these plots that I showed in this figure, you can, generate them. And in addition, so right now with Bernardo Zan, we're looking at deforming ON bootstrap solutions in N. So that's another result that should be coming out at some point. So if your worry is that I'm making promises and I'm not going to carry them out, I mean.
No, I think I'm not. Maybe it sounded more accusatory than it really was meant to be. It was more like the question is implicitly, like, is there a qualitative difference between what they were doing back in the day and what you're doing?
I think it's very similar. I think they had maybe something more sophisticated where they were linearizing near the extremal functionals, and that allowed them to flow and so on. And I think maybe the reason other people beside Miguel didn't pick that up was perhaps, I mean, I'm speculating here, was perhaps because it was written in Julia. I'm not sure.
I was not asking you to make sociological comments.
Right. I think it's qualitatively similar. We are, in fact, I think we might be solving the same set of equations. I'm just repackaging it in terms of Lagrangians because it's easier for me to keep track of, the number of variables in equations. I think in principle, it's very similar.
Okay, thank you. That was helpful.
Yeah, okay. All right, since I'm out of time, let me just do a quick summary and talk about some future directions. So, I described some procedure to deform the extremal solutions. It's much faster than STPP. It applies to non-unitary theories, and it's parameterized directly in terms of the CFD data, which might be helpful. If you know something about the CFD data, you might be able to directly move in those directions. There's nothing to say that you have to deform with the external dimension or central charge and so on. And the difficulty I described is it's difficult to find initial conditions. In fact, I don't know any way of finding initial conditions besides using STPP itself, except maybe there was a talk given at the collaboration where people were using some sophisticated black box reinforced learning thing for finding solutions to these equations. Perhaps something like that could be employed to find initial conditions. I don't really know too much about it. And the other thing that I hinted to but didn't really discuss is that not all initial conditions result in viable deformations. Sometimes, no matter what you do, you start with some initial conditions and you try to deform it, and the deformation just diverges and you're not able to continue. It could be that you're not seeing the double zeros that appear, so it never crosses zero, and you don't know what roots to add. That's one possibility. The other possibility is that these solutions are just not connected. I don't know what the answer to this is, and it's worth exploring. What initial conditions you're able to deform, have large deformations, and so on. And are these extremal functionals unique in any sense? And is there features and so on that you can try to latch onto to say that there exists a theory here or there. You should explore these deformations with higher lambda, which requires implementing what I was describing, automatic detection of new roots that get added. You can try to deform with respect to other parameters, delta phi, D and C is what we tried here. They seem to function to some extent. I'm trying, there's some ongoing work where we're trying to deform N and ON models. Is it possible to deform the islands? Something I didn't describe, and I suspect I won't have time to describe, is detecting 2D CFDs by searching for integrality of the degeneracies that appear in the partition function. We can talk about that if people are interested. And this last point is the point I've already made. Is there any features you can try to find in these deformations that help you detect whether you actually hit a theory or not? So that's it for me. Thank you. I'll answer questions if people have them.
Thank you. Any further questions?
I have a kind of a comment. I think compared to what Miguel did, this work, which I think is quite amazing, is that it has one important advantage, is that it's somebody else, but Miguel did something about it. I think it's for the first time. Well, of course, you already had the previous work on modular Bootstrap, which was quite impressive. But I think the story of how operators recombine, new operators appear, and so on, I think it was always very worrisome to many people, including myself. And so that you see that, in fact, it's not so worrisome, that you think it's doable. I think it's a good sign. Okay.
Good. I mean, I was hoping to, lower the barrier of entry. It's like, because every time I thought about doing this, I was thinking that I don't want to do a lot of coding, but at some point I got interested enough to sit down and do the coding, but hoping that sharing the code with the community will help people, who want to try.
When there's a killer app, what's the killer app for these techniques, right? Okay, there are many techniques.
Yeah. Well, one, I think
problems. So OAN is an interesting problem.
ON is an interesting problem, which we're trying with Bernardo. And also, I think speeding up finding the islands might free up a whole lot of CPU hours.
About that, I wanted to comment that again, there is also similarity between your philosophy and it would be how does your philosophy compare to the navigator function?
I think the navigator function still uses, there's a function that they optimize that lets them go, like, I'm not an expert on this.
They includes me, so.
Right. So this function that you guys use, maybe you can tell me. Do you guys still use semi-definite programming?
I think this, there is some interesting similarity and difference is that, so navigator function can indeed be seen as a cheap version of what you're doing. Okay, I mean, cheap, why do I call it this cheap? Is that when you do navigator function and you go around the island, so we have the algorithm which allows us to go explore the boundary of the island and very quickly to find maximal, minimal. That was done by Martin, demonstrated in his recent paper on 3D easing. So when you do it with the navigator function, the issue that sometimes when you go around the island, the zeros of the extremal functionals are expected to collide, new zeros to appear, and so on. These issues, they show up in the fact that the navigator function is not an infinitely smooth function.
Yep.
But the optimization methods that you use when you work with the navigator function, you use some optimization methods, you apply gradient descent and so on. Those empirically, those optimization methods are not very sensitive to some mild discontinuities in high derivatives of the navigator function. So you can still treat this navigator function as smooth, even though it's not actually smooth. So you don't have to worry about monitoring where the zeros are, in certain research, you just like follow one scalar quantity and you can still map out the boundary of the island in that framework. So it provides a speed up compared to just some scans, a significant speed up compared to scans.
I see. And you suspect the phenomenon is the same as new zeros, new single roots appearing.
I'm pretty sure that this is related. So where would the navigator function be non-smooth? Only where something happens with the zeros of the extremal function.
Right. Then I would suggest, parametrizing this problem in terms of the roots will perhaps give you a better handle on how to handle these discontinuities.
We already feel that we have a very good handle with the navigator function. So the problem is that you have to find a killer app. You have to find the killer app for you to.
I see.
So you have to see what other people can do and say, okay, I think I can do something else that you guys cannot do.
Fair enough.
That's the only way to convince people that your method is.
Yeah, fair enough. I mean, I'm speculating, but I think there's a chance.
But let me finish with something positive. I think you were very modest about interpreting this evidence that the Li Yang that you seem to be finding is there. So
I mean, this is the Bootstrap collaboration.
I think you could claim it with more confidence that it should be that it's really Li Yang. And
yeah, I think what I was just trying to, when we say the Bootstrap bounds are rigorous, we really mean they are rigorous. Whereas in this case, it's I couldn't make. I was using those standards to make the claims that I was making. But yeah, I personally believe that this is good evidence for this. I agree with you.
So is there something special about that particular point? Maybe stress tensor. Does stress tensor exist everywhere, conserved one, or does it exist only in that square that you were, where the Li Yang is?
No, there is an operator of spin 2 at the unitarity bound across the entire flow, which is why I can plot the central charge across the entire deformation.
Okay, thanks.
Can you do that in 3D? Can you find Li Yang in 3D?
I mean, that's sort of what I was claiming I was doing. Sorry, the slides went away. In 3 dimensions, that's what I claimed I was doing, which was to go with 2 different starting points to what I was calling, maybe I should call it the 3D Li Yang, but Yeah, these plots are in 3D. So there's two different deformations that seem to pass through regions where people expect there exists a 3D non-unitary theory.
Yes.
And then maybe the task to do is to go to 6th dimension where, I know everything about that theory.
Well, even in 3 dimensions, I think the critical exponents are reasonably well known.
Yeah, this is true. Yeah. So I think maybe one thing to try to go to higher and higher lambda and see how well you agree with those people. But then, I would say those, like the Monte Carlo and the epsilon expansion people, have a better claim to having the correct result than me in this case. Maybe because it's not rigorous in the sense of the unitary bootstrap.
Any other questions?
I still would like to, why is this so not rigorous? Why are we suddenly having these huge, standards of rigor? You have a truncated solution to crossing with relatively few operators in that region that you can control. You can systematically improve by increasing lambda. It's not a bound, but it's a solution to crossing.
Yeah, that's all I mean. That's all I mean. That's all I mean by saying it's not rigorous. It's not a bound, but it's some solution to the truncated crossing equations. I agree, and I agree, and that's all I meant.
Okay. Anything else? No, we can thank Nima again. Thanks.
Thanks,
We'll
guys.
see you next week.